This lesson is to evaluate exponential functions and identify and graph exponential function. The table and the graph show an insect population that increases over time. Day 0 was 2, 1 was 6, 2 was 18, and 3 was 54. The population is being multiplied by 3 each day. You can see on the right that the graph is a curve going upward. A function rule that describes the pattern above is f of x equals 2 times in parentheses 3 raised to the x power. This type of function, in which the independent variable appears in an exponent, is an exponential function. Notice that 2 is the starting population, and 3 is the amount by which the population is multiplied each day. An exponential function has the form f of x equals a times b raised to the x power. A cannot equal 0, b cannot equal 1, and b has to be greater than 0, or a positive number. The function f of x equals 500 times 1.035 raised to the x power models the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? So we're going to write the function f of x equals 500 times in parentheses 1.035 raised to the x power, and we're going to substitute 6 for x. So we get f of 6, the function of 6, is 500 times 1.035 raised to the 6th power. You're going to evaluate 1.035 raised to the 6th power. You always do the power first. And you get 1.229. Then you multiply that by 500, and you get 614.63. So there will be $614.63 in 6 years. The function f of x equals 200,000 times 0.98 raised to the x power, where x is the time in years, and it models the population of a city. What will the population be in 7 years? So we're going to substitute 7 for x into the function. So we get f of 7 equals 200,000 times 0.98 raised to the 7th power. We're going to use a calculator, and we're going to round to the nearest whole number to make it easier. So 0.98 raised to the 7th power, and then multiply by 200,000, and we get 173,625. The population will be about 173,625 in 7 years. The reason why we round to the nearest whole number is because obviously there's not going to be part of a person. The function f of x equals 8 times 0.75 raised to the x power models the width of a photograph in inches after it has been reduced by 25% x times. What is the width of the photograph after it's been reduced 3 times? This one's for you to try on your own, and then you can check back for your answer. So we're going to substitute in 3 for x in the function, and we get f of 3 equals 8 times 0.75 raised to the 3rd power. We're going to use a calculator. We're going to take 0.75 and multiply it to itself 3 times, and then multiply that by 8, and we get 3.375. So the size of the picture will be reduced to a width of 3.375 inches. Remember that linear functions have constant first differences and quadratic functions have constant second differences. Exponential functions do not have constant differences, but they do have constant ratios. So if you're looking at a table, the x value has to change, so you can see that it goes up by 1 each time. And then the function value, or the y value that you get, will be multiplied by the same thing each time. So it will have a constant ratio. As the x values increase by a constant amount, the y values are multiplied by a constant amount. This amount is the constant ratio and is the value of b in f of x equals a times b raised to the x power. Tell whether each set of ordered pairs satisfies an exponential function. Explain your answer. 0, 4, 1, 12, 2, 36, and 3, 108. So we write it as a table, 0, 1, 2, 3 in the x column, 4, 12, 36, 108 in the y column. Each time you're being multiplied to 3, so there is a constant ratio. We also need to make sure that x is changing each time, and it is by 1. So this is an exponential function. The x values increase by a constant amount, and the y values are multiplied by a constant amount. Tell whether each set of ordered pairs satisfies an exponential function. Explain your answer. -1, -64, 0, 0, 1, 64, 2, 128. So we write it in a table, -1, 0, 1, 2 in the x column, -64, 0, 64, 128 in the y column. So we check for a constant change in x. It's increasing by 1 each time. And then we need to check for a constant ratio. It's adding 64 each time, but we needed it to be multiplying. So this is not an exponential function, as the x values increase by a constant amount, but the y values are not multiplied by a constant amount. Tell whether each set of ordered pairs satisfies an exponential function. Explain your answer. -1, 1, 0, 1, 1, 1, and 2, 4. This one's for you to try on your own, and then you can check back for your answer. So writing them in a table is probably easiest. So you have -1, 0, 1, 2 in the x column and 1, 0, 1, 4 in the y column. You check for a constant change in x, and there is one. It's increasing by 1 each time. And then you check for y to see if it's being multiplied, and there's not. It's -1 plus 1 and plus 3. So this is not an exponential function, as the x values increase by a constant amount. The y values are not multiplied by a constant amount. Tell whether each set of ordered pairs satisfies an exponential function. Explain your answer. We have -2, 4, -1, 2, 0, 1, 1, and 0.5. This one's for you to try on your own, and then you can check back for your answer. So written in a table, the x values would be -2, -1, 0, 1, and the y would be 4, 2, 1, and 0.5. So we check for a constant change in x. It's increasing by 1 each time. And then we check to see if there is a constant term being multiplied, and we get times 0.5 or 1/2 each time. So this is an exponential function, as the x values increase by a constant amount and the y values are multiplied by a constant amount. To graph an exponential function, choose several values of x, positive, negative, and 0, and generate ordered pairs, and then you plot the points and connect them with a smooth curve. So if we're going to graph y equals 0.5 times 2 raised to the x power, we're going to choose several values of x and generate ordered pairs. So we're going to choose -, 0, and then a couple positives. So they chose -1, 0, 1, and 2. We're going to plug -1 in for x, 0 in for x, 1 in for x, and 2 in for x, and we end up with 0.25, 0.5, 1, and 2. So when we plot them on a graph and then connect those dots, it should form a smooth curve. Graph y equals 2 raised to the x power. This one's for you to try on your own, and then you can check back for your answer. So we're going to choose several values of x and generate ordered pairs. So if we chose -1, 0, 1, and 2, and then plugged in those values for x into the equation, and we would get 0.5, 1, 2, and 4. When you plot them on the line, they should form a smooth curve, and you would connect the dots. Graph y equals 0.2 times 5 raised to the x power. This one's for you to try on your own, and then you can check back for your answer. So we're going to choose several values of x and generate ordered pairs. So the x values -1, 0, 1, and 2. When we plug in for x to the equation, we get 0.04, 0.2, 1, and 5. When the numbers are like that, you just have to kind of estimate where they would be on the graph. So then you plot your points and then connect them with a smooth curve. When you graph y equals -1/4 times, in parentheses, 2 raised to the x power, we're going to still choose several values of x and generate ordered pairs. We still chose -1, 0, 1, 2. We got -0.125, -0.25, -0.5, and -1. So when we plot those, you'll notice that in this one, the curve is now going downward. And we're still going to plot those, estimating where they would go on the graph, and then connect them with a smooth curve. So if we're going to graph y equals -6 raised to the x power, I want you to try this on your own, then you can check back for your answer. So we're going to choose several values. Again, -1, 0, 1, 2. This time you'll notice that we have negative numbers, so we have negative 0.167, negative 1, negative 6, and negative 36. So we're going to estimate where those would go on the graph. You'll notice that this graph is curving downward, and so we'll plot those points and then connect them with a smooth curve. Graph y equals negative 3 times in parentheses 3 raised to the x power. This one's for you to try on your own, and then you can check back for your answer. So we choose several values of x and generate ordered pairs, negative 1, 0, 1, and 2, and then we plug it in and we end up with negative 1, negative 3, negative 9, negative 27. So we're going to graph the ordered pairs and connect them with a smooth curve. You'll notice again, because the values are negative, our curve is going down. Graph each exponential function. Y equals negative 1 times in parentheses 1/4 raised to the x power. So we're still going to choose our x values, negative 1, 0, 1, and 2. And we end up with negative 4, negative 1, negative 0.25, negative 0.0625. We're going to graph our line, and you'll notice this time that the curve is coming from the right-hand side instead of the left-hand side, and it is facing downward because our values are negative. So we're just going to estimate about where they would go, and then you connect your dots with a smooth curve. So we have y equals 4. We're going to graph y equals 4 times in parentheses 0.6 raised to the x power. And we're going to choose our values negative 1, 0, 1, and 2. And we're going to get 6.67, 4, 2.4, and 1.44. And then you'll notice that this time the graph is now curving upward, but it is still coming from the right. So we get to estimate where those points would go and then connect them with a smooth curve. Y equals 4 times in parentheses 1/4 raised to the x power. This one's for you to try, and then you can check back for your answer. When we have our chart, we have negative 1, 0, 1, 2, and when we plug those in for x, we get 16, 4, 1, and 0.25. So we're going to estimate where those go. You can see that the curve is going up, but now it is coming from the right-hand side. And then we connect them with a smooth curve. Graphing y equals negative 2 times in parentheses 0.1 raised to the x power. This one's for you to try on your own, and then you can check back for your answer. So you're going to choose your values of x, and we get negative 1, 0, 1, and 2. We plug those values in, and we get negative 20, negative 2, negative 0.2, negative 0.02. And we graph. You can kind of estimate where those dots would go. And then you'll see that the graph is coming from the right-hand side, but it's curving down now because the a value was negative. This box summarizes the general shapes of the exponential functions. If a is greater than 0 or positive, then the graphs will curve upward. If a is less than 0 or negative, then the graph will curve downward. You may have noticed that pattern from the examples that we did. For y equals a times b raised to the x power, if b is greater than 1 or a whole number larger than 1, no fractions, then the graph will have one of these shapes. They will be coming from the left-hand side. For y equals a times b raised to the x power, if b is greater than 0 but less than 1, so a fraction or a decimal number, then the graph will have one of these shapes, and they will be coming from the right-hand side. These are patterns you might have noticed from the examples that we did.